variable, that is what we're going to add. For multiplication and division, we're going to add the fractional uncertainties. And I know it's a bit weird because it's not change in, we show an uncertainty with delta z as well, because it's kind of the change in the value, if you think about it, because it would be plus that or minus that, and therefore you could actually see it like that. You guys are please going to have to tell me if I'm again. I'm hoping that you can all be fine, but shout if something happens. All right. Then if there's a power, it's the same as having the value more than once. So it would be the same. So if it's x squared, yeah, it's stalling a lot. It's like lagging on my side. All at once. X squared. Guys, is it lagging this much on your side as well? Can someone tell me if you can hear me properly, or is it lagging? Okay. Then I'm just going to carry on. Alright, so for x squared, that's the same as saying x times x. So that means if we are going to do the uncertainty in x squared, it's going to be the uncertainty in x. Okay, now when I'm writing, it's actually not showing. It's coming through, so I think it's just the board, it's just the whiteboard. Let me just fix that. Yeah, I think that's better. Great, that is better. If I have x squared, that's the same as saying x times x. Let's doing it again. Anyway, so that means if the uncertainty in x is plus minus whatever 5, then you're going to say uncertainty in x over x, remember, so that will be the 5 over whatever the value is, plus, because we're going to add the fractional uncertainty in x over x. And this means that is just the same as saying 2 times the uncertainty in x over x. So we did that day at the tuck shop, but we didn't do this in class. So that means you could have written it to the power of 2. So if you have a power, this is why the power just becomes a multiple of that uncertainty. So you're just going to use the uncertainties. It's just kind of a weird way of writing it, but you can see that the n just goes into the front there, and that's how you do that, but we will look at that. The average we don't really use so much. I don't know if you've done it in maths yet, but these straight lines means absolute value. So the absolute value of the average, and then that divided by the number of values that you actually used squared. But this one you will not really get. We won't be asking that one in your exams or tests. Alright, so then yes, the exercise that you were supposed to do is this one, exercise 3. So we're going to quickly do this and practice these skills, and then we're going to move on to graphs if we have some time left. So for this first one, it says the sides of a fence are measured with a tape measure to be 124,4 centimeters. Now they tell you the uncertainty is 0,07. Now there is a problem in that, because if you're looking at the values, you've got 1,24, why did I do a comma there? I've got no idea. 124,2 plus or minus, and then it's going to be 0,07. So you can see that they made a mistake in this, because the uncertainty cannot sit further than your last digit that you could measure with your piece of apparatus. And we always say if it's a meter rule or something, the uncertainty is in that value or half that value. That means they should have given us that second digit, or this uncertainty will just have to change and say it is the smallest reading that we can take, and so I want you to just change that into 0,1. because that would be a correct way of writing it, plus or minus 0.1. So remember the values. So sorry for the ones that did this already with those values, but you can just, I'm hoping that you can see that that is not really right, because there's where our uncertainty is lying. And our value and our uncertainty must always be to the same number of decimal places, because it comes from the same piece of apparatus. So that part there, we definitely need to fix. Then they say calculate the measured perimeter, including its uncertainty. So if they're saying perimeter, so that means it's the side 1, 2, 3, 4 sides. Okay, I'm just making random sides because they did not say that it is a square. Then they could have given us the same sides. So now all we're going to do to get the perimeter, remember to get the actual value, you don't worry about the plus minuses. We're just going to say perimeter is then going to be the 124, and I want, if you haven't done this, I want you on your calculators, 124,2 plus 222,5 plus 151,1 plus 164,2. And what did that give you as an answer? You can type, you can scream, you can do whatever you feel like doing. I will look at the answers if you are typing. Give me an answer for that value quick. Yes? I didn't hear that. 662. Thank you. On the dot. Is there no comma? Great. But because now that we can practice that as well, because these values all had 4 significant figures, you're going to have to give your answer to 4 significant figures as well. So that would be the correct answer then in centimeters. Now we are going to get the uncertainty. So now the uncertainty in the perimeter is going to be the uncertainties in all these values, but because it's plus, it's going to be the actual uncertainties. So it's just going to be 0,1 plus 0,1 plus 0,1 plus 0,1, and that will just give us 0,4. And please, that is never your final answer. You always have to say, therefore, my actual perimeter, and now you're going to give it with a value and the uncertainty. So my actual perimeter is 662, 0 plus or minus 0,4, and all of that is measured in centimeters. Okay, please remember that you don't have to put the brackets, but it just makes it neat and you can see what the centimeters applies to. Okay, so if you didn't use the 0,1, that's fine. You would have just had 0,7 times 4, so your value here would then have been 662, 0 plus or minus. But that's adding random zeros with no purpose, because then we're going to have to do that because our uncertainty would have been 0,28, I'm assuming. Yeah. And that is why I would have to have 2 decimal places, because my uncertainty is 2 decimal places. Please, if you left it like that, and you can see this looks clumsy because we're adding random zeros with really no purpose, and we don't like doing that. And that is why I wanted you to change that value. Any questions about 3.1? Okay. If I don't hear anything, I'm just going to assume it's all good. And we've got 3.2 then. Then they say we've got a rectangle, and the sides is that, and this time we want the area of the rectangle. So now remember, and again they did that. I don't know why they did that. This should also be 0,1, not 0,07. This is very weird. I'll let him know that we need to change that. Okay, please, that is a very, otherwise you must add random zeros there with no meaning, and we don't like doing that. So we have to say, when we do this area, again, we're going to say area is equal to length times breadth, and that is just going to be 15,3 times by 9,6. And can someone please type the answer or tell me what the answer is? I don't know why I'm battling to hear you. Just say again for me, please. 246. Okay, thank you. Thank you. 146,88, and that is now in centimeters, but this is now centimeters squared. Please, again, don't worry. I was marking that the year one exam that the other guys wrote, and a lot of them are putting the plus and minuses in the calculation. That is just unnecessary and it's confusing things. We're going to work out the uncertainty in the area afterwards. And because this was multiplication, it's going to be the fractional uncertainty in the length. So changing length over length plus the fractional uncertainty in the breadth. And that is then going to be 0,1. I should use the 0,07. It just goes against my grain though. If you use the 0,07, it's fine. Just mark your method. It's not going to be the same. But if not, please fix it. Over 15,3 plus the 0,1 over 9,6. And that gives you the fractional uncertainty, or that gives you this gives you the fractional uncertainty in A. So the fractional uncertainty in the area is equal to the fractional uncertainty in L plus the fractional uncertainty in B. But that is not what we want. We want the actual uncertainty in the area. And that is why you have to take these fractional uncertainties that you calculate and times it by the actual area answer. Okay, so you're going to then multiply the fractional uncertainties, which is 0,1 over, I'm just going to write it again, plus 0,1 over 9,6. You could have written it here already. I just want you to see when you're checking your work for the exam or for the test that we're hopefully going to write this term, that you are going to multiply by the 146,88. And now this is going to give us the absolute uncertainty in the area. So can someone please work that out for us? I need to get my calculator out as well, but I'm sure I can trust you guys to do this correctly on your calculators. Let's get an answer. 2,49. Did everyone get that? Centimeters squared. All right, now this is not our final answer. Remember, once we've done that, we have to say area equals, and now we have to put our answer combined again and say 1 and now before we even do that, we can go back here and say, look at the number of significant figures. How many significant figures are there? Everyone should scream at me. How many? 15,3 means there are 3 significant figures. Digits after the comma counts. So there are 3 significant figures. That means we should have rounded this value off to 147. And if this is to the closest real number, then if there's no digits after the comma, then this value here would then become 2, not even 2,5. This is going to become 2 centimeters cubed. Oh, squared. When you're writing your A value, it's going to be 147 plus or minus 2 centimeters squared. And you can put that in brackets again. And that is our final answer. Does everyone understand why I wrote 2 and not 3? We only look at this number when we are rounding off this one. I'm not going to look at the 9. If I was going to go to this digit here if I was going to leave an extra digit after the comma. And often we allow three significant figures or one more. Just because you always get taught in maths that it's more accurate. It's not really, because our apparatus couldn't measure that. But that is why we would rather not. You don't do that. But if you do 2 comma 5, then there would have to be a comma 0 in this value. But it's, again, adding a random 0 with no meaning, because we only had three significant figures in the raw data. Whatever we use in the raw data, that is what we use in our answer. Everyone happy with 3.2? No, see, that's the thing with real values in maths. They teach you to leave it in fractions because they say it's more accurate. It is more accurate because it's an abstract value. This is an actual reading that you are using a ruler to measure. You cannot use your ruler and measure to that decimal place there. And now once we have gone from centimeters to centimeters squared, it actually becomes less, the values become less accurate because we are now squaring values with an uncertainty already in them. So that is why we always have to look at the significant figures in our values. And because there were only three significant figures there, we cannot have an answer with more than that, because we cannot calculate this area with the values that we take with a real life ruler more accurately than this. So that 0.88 actually isn't significant anymore, because we couldn't actually measure it to a number, to some form of accuracy. We could only measure three significant figures with the ruler that I gave you. Actually, if we look at it here, we have two significant figures here. But because this is the decimal place here that they could measure to, I would say we could get away with the three significant figures there. If you follow proper rules, it would mean that you would have had to use the two significant figures, because we're looking at the least number of significant figures. And if we wouldn't use the uncertainty for that, it would only be for real values. Does that make sense? Okay. In maths, it's very different. All right, next question. We've got a ball that drops from rest, unknown height. The time it takes for the ball to hit the ground is that. So they're giving you, that looks good to me, because there's the decimal place, there's the uncertainty. The height is related they're giving you the equation, they're giving you g. Remember, this is a constant on your information sheet, so we're not going to use that to determine the number of significant figures, although in this case it was one of your given values, so then we should. Assume that if they didn't give you g in the question, you would refer back to your information sheet, and then you would ignore the significant figures in the constant that you get from your information sheet. Assume that the value for g carries no uncertainty, and calculate the height including its uncertainty. All right, so let's see what we're going to do. We're going to say the height is equal to. Now remember, when you're doing that, again, forget that you have anything like an uncertainty. So it's just going to be half gt squared. And it doesn't even matter that you haven't done this yet in core physics. You're just going to take your, like half of physics is just choosing an equation, substituting some values in there, 9,81, and then t, oh no, not t is given to us as 1,3, and please don't forget the square. So often people forget a square from there to there, and you can all calculate the height for me. You can type or scream. It would be nice to hear the answer from anyone. Great. Oh, that happens so often. Please, please, guys. It's a common mistake in exam stress that happens all the time. Okay, and this is a height. So what are we going to put the unit as? Yeah, height is just in meters. And if you were wondering why we're using meters and not centimeters, you go and look at your constant. Yes, because that's meters per second, and therefore our answer will be in meters as well. So that is our actual answer. And now we're going to have to get the uncertainty. So what you need to think is in this equation, which values there had an uncertainty in it? The half is a real number, so that doesn't have an uncertainty in it. They told us that G does not have an uncertainty in it, so we can ignore G. So the only thing that contributes to the uncertainty in H is the T. So that means, and we multiplied it. So that means that the uncertainty in H, the fractional uncertainty in H, is going to be the fractional uncertainty in T. But because there's another T, it's going to be plus another fractional uncertainty in T. And that's where that other rule comes in. That says instead of writing it twice, because sometimes there's to the power of 5, we're not going to write it 5 times. Instead of writing it twice, we're just going to say 2 times the fractional uncertainty in T. And now we can fill in our values. So we know that the uncertainty in T is, or the fractional uncertainty is 0,2 over the 1,3. And we can then multiply that, do that on your calculators, and you can give me an answer again. Perfect. Is that it? Give me? Okay, so that's enough, yeah. Because now we need to think. How many of these are we actually going to write? Because are we looking at significant figures? Oh, and also, this is still the fractional uncertainty in H. So to get the actual uncertainty in H, we have to take that value, and you can leave it in your calculator, 2,55046, whatever you had. That you need to times by your actual height value, which is 8,29. So just times it for us on your calculator, and that will give you the actual uncertainty, or the absolute uncertainty in H. Did you already multiply it by 2? So let's fix. We could jump straight into the absolute uncertainty. Yeah, maybe that's. Zach, is that what you did? Okay, so you actually gave us the value that you gave us was already this answer, 2,5046. So the absolute and the uncertainty here was the naught comma, what did you guys get? Naught comma 3 something? Okay, and then you multiply that by your actual value of h, and does that give you the 2,55046? Okay, great. So that means that is our actual answer for the uncertainty. So it is the right value that we are looking at. But now we need to decide. in our value here with our three significant figures, we ended up having 2 decimal places. So that means our uncertainty must also have the same number of decimal places as our value there. So that means we're going to throw away all of that, and we're going to give our real answer for h as h is equal to 8,29 plus or minus 2,55, and all of that is going to be in meters, and that is then our final answer. Sorry, it's a bit squashed, yeah? And that is then our final answer for h. Okay, so please remember, so you actually all did it right in the end. You don't have to show this answer because it's a place where you could have a rounding error, and then that rounding error becomes another rounding error here. So you don't have to have that, but if you do, it's all good. Okay, and then we've got the last two. 3.4, they want to know, calculate the uncertainty in the value of the area of a circle that with a radius of that. Okay, now you need to know the formula for the radius of a circle. So if we're looking at 3.4, the formula for the area of a circle. What is the formula for an area of a circle? Pi r squared. So again, to get that value, you are just going to use your normal values, pi on your calculator, and r you're going to use your value that they give you there, 0,146, and that's going to give you your value for the area. This normally just counts 1 mark, sometimes another for the significant figures, but plug and play, we're assuming that you can do that when you made it this far. So please give me an answer for the area. Okay, now this answer, if you want to write it as the correct number of significant figures, I would say you could go scientific notation. It's fine if you don't, but then you're going to write it as, remember here we've got 3 significant figures. So if we are looking at 3 significant figures, these zeros don't count. So our 3 significant figures are the ones that sits there. So you could have said 6,6. No, that'll become a 0. So 670. Or you could then write times by 10 to the minus 2. Or you can round it and say this is 0,06. And then if you make that a 7, the 0 should stay because it has to have 3 significant figures. That's why it would maybe be better to write it as 6,70 times by 10 to the minus 2. Both of these will be accepted though for your answer. Okay, you didn't have to do it there, you can do it in your final answer. But now we need to get the uncertainty. Oops, I hope you didn't do what I did. Can you see I did it again? Thank you. Alright, I often do that, and it's a common mistake that we find. Alright, now we've got our value, but again the r was squared. So that means to get the uncertainty in the fractional uncertainty in our area, we're going to say that it is going to be the fractional uncertainty. So it's 0,005 over 0,146. I'm going to do this a little bit faster now. And we need 2 of them because it's squared. So we're going to need 2 of these. And then I'm just going to shortcut that step and take the a to the other side and say we're going to multiply that by, remember you're going to still have this value in your calculator, so just do it in, if you can keep a value in your calculator and not make rounding errors, it is always going to save you time in core physics as well. So that value, I would never write something like that down really, because it is in your calculator still from there. And that will give you actual uncertainty in A. So all of you please type that in and see if we all get the same answer. You can type or shout again, anyone? So because, yeah. Okay, you can leave it there because I know those are not going to be used. Now, what's important is whatever you did here is what you need to do here. If you use your decimals, you need 1, 2, 3, 4 decimal places. So that means you would have to, in your uncertainty, also have 4 decimal places. So that means we're going to have to use all of that. So this would be 0, comma, 0, 0, 4, 6. So that's the one way that we can write our answer. We could say that if we're using that, we can say that A is equal to, that means it's these two go together, the ones with the stars now. So 0, comma, 0, 6, 7, 0 plus or minus 0, comma, 0, 0, 4, 6, and all of that is then centimeters squared. I still think a less clumsy way of doing it would be to say that this is going to be 6,70, and then you're just going to do the same power of 10. The uncertainty and its value has to be to the same power of 10. So 1, 2. So this will be plus or minus 0, comma 4, 6. And you can see much less zeros. So the answer already looks better. And both of these values, and this makes it look beautiful, because now both of these values have a power of 10 to the minus 2. So you put your 10 to the minus 2 applicable to both of your values outside of the bracket. And then you put your centimeters squared. So this is the preferred way of writing an answer. If there are 0,000, we don't like clumsy zeros. So this would be definitely the best answer, which is based on this one here, and I didn't write that one there. Okay, I hope you all follow that one. Any questions on that one? And then we've got one more left. It says the force exerted by the gas on that is, and they're giving us an answer in a value in millimeters, and they're giving us the force. So they say calculate the uncertainty in the area of the piston, and then the uncertainty in the calculated value of the pressure. All right, so they're giving us the radius. So that means we are assuming that it is circular, and we can use the area equation again. So for A, we're going to do the same thing. We're going to say area is equal to pi r squared. It's equal to pi. The radius is given to us as 8 and squared. And you guys can get that value for me, please. I feel so lazy not getting my calculator out. I don't know where in this bag it is. So you will be my calculator people for the night. Okay, again, a long value. We won't round this off too much yet because it's far from, oh no, it is the answer for A. So for A, we will round it off because if you're looking here, how many significant figures do they give us there? Remember a zero after a comma counts. Be careful. It's one of the traps that's good for you. So that zero counts. If it was a T, then it would be 1 because the zero wouldn't count. But as soon as it's after a comma, then it will count. So it's actually 2. Okay, so that means we're going to have to write this value to two significant figures as well, but that's a little bit difficult, because if we're rounding it off to two significant figures, it means it's this digit here. So that means the answer is going to be 200. But this is not actually significant. So that means that we're going to have to write it in scientific notation and say that this is 2 comma 0, and that will be times 10 to the minus 2 centimeters, no, millimeters squared. So that is going to be our real value. And then again, for the uncertainty, it's exactly the same as in 3.4. We're going to say that the uncertainty in the area is going to be equal to 2 times the uncertainty in the radius, which is 0.4 over 8, 0. And to save time, we're going to skip this step where we write it there, and it will be times by 2, 0. Now, if you kept that in your calculator, that is absolutely fine. And if you even write it in the exam and write that 201,0619, keep some decimal places there, it's also absolutely fine. And then you use that to calculate your uncertainty in A, absolute uncertainty in A. Tell me what you're getting. Okay, again, lots of numbers there that doesn't really have any significance, because we could only actually read two decimal places. And that is why we need to round this one off to two significant figures as well, which again would be two. Let's see, now it becomes weird, because two significant figures would be 20. But then if I write 20, that's actually only one significant figure. And that is why I have to write it as raw, and it's always, we need to try and get the, not try, we have to get the powers of 10 the same. So we're going to move this, so we're going to also call this 0.2 times 10 to the minus 2. Make sure that your power of 10 for your uncertainty and your power of 10 for your calculated value is the same. And normally you'll see that will give you an unclumsy, if that's a word, answer. Because now we can write A is equal to, and it's going to be 2, 0. We've got our two significant figures, plus or minus 0.2. We're going to put it in brackets, and we're going to say times by 10 to the minus 2 before we put the, sorry, I'm going to just wipe that all out before we put our millimeters squared. Okay, I hope you get this whole power of 10. Yes, absolutely. I was hoping for that question. If you go back to when we had this here, 0.2 is just one significant figure. But the rule for uncertainties and its values isn't actually significant figures. It's decimal places. Because if I could read this value up to that accuracy there, it means my uncertainty sits in this value. So when you're going from a value to its uncertainty, the uncertainty must follow your value when it comes to decimal places. The significant figures here is determined by your raw readings. So significant figures comes from raw readings. So the significant figures in your real answer. Your decimal places in your uncertainty comes from the decimal places in your actual answer. Very important thing to note. Thanks for the question. And then just remember to, like I've left out here now, just remember to add the units, millimeters squared. Okay, must have a unit, otherwise it's wrong. All right, and then they want to know the pressure. You haven't really done pressure, Pressure is force over area, but that would mean that the area is the only thing that has an uncertainty. So that means the area would determine the uncertainty in the force. So let's just finish this last one as well. Then at least we've done all the questions tonight, and we can start with graphing on Friday. If we now go and get the pressure, we can say that pressure is equal to force over area. And then the force is given to us. Yes, the force was given to us. So you're going to say that's 30 over 2. But now here is something that you haven't really done. So we will never work in millimeters for pressure. Pressure is always going to be force over area, but that area needs to be in meters squared. Now let's see who can remember how we're going to change from millimeters squared to meters squared. What must I do? Times 10 to the what? Millimeters to meters. So it can't be a positive power, it must be a negative. Yeah. Guys, that's the things we started this year off in your normal physics. Let me just refresh your memory. Milli is times 10 to the minus 3. But because there's a 2, remember it's going to be then 2 times minus 3, which gives us the minus 6. Yes, that is perfect. So this is going to give us an answer of 1 comma 5 times 10 to the power of, I've got no idea. I should. Minus 5. Am I right? Oh, of course, it goes to the top. It's 15. Yeah, that is right. And this then will be newtons per meter squared. So that's my answer for the pressure. I just want to clean this up a little bit for us. We don't need that anymore. We just need the area now. So now if we go and look at our area, at our uncertainty, we can say that our uncertainty in the pressure, again, the fractional uncertainty in the pressure is going to be the fractional uncertainty in the force, because both of those value carries an uncertainty. Sometimes one of them doesn't, but in this case they both do. So it's the fractional uncertainty in F plus the fractional uncertainty in the area that we've just worked out in the previous question. That means this one was given to us as 2 over 30. And you can see this nicely now, because these are newtons and these are millimeters. We can never add apples to bananas, and that's why we have to actually work with the fractions. So this one here plus the 0,2 over 2. Why don't I have to care about the powers of 10 in the units? When I use the fractional uncertainty, why am I now using 2 and 0,2 and not times 10 to the minus 6 or whatever I did earlier? Why can I throw it away? Okay, look, if I write the 0,2, remember the times 10 to the 2 and the millimeters applied is applicable to the 0,2. So you can say here times 10 to the 2 millimeters squared. So now, yes, we can change it all to the power of 6 and do all the magic there with the numbers. But at the bottom, we've got exactly the same thing. 10 to the 2 millimeters squared. So does it, because it's a fraction, I don't have to worry about anything about, as long as the numbers are in the same units and its uncertainty is in the same units, I don't have to worry about changing it, because the fraction or the percentage is going to be exactly the same, because that and that is just going to cancel each other out. And we end up with, and that is why this is so valuable to write it to the same powers, because that means that you can just use the fraction as it is and it makes your life way more simple. And that is going to be our fractional uncertainty in the pressure. But if we want the actual uncertainty, remember then we have to say actual uncertainty in P is then going to be the fractional uncertainties times by, and now this value must be in newtons per meter squared. So that must be in the real unit. So 1,5 times 10 to the 7. And this will give you now our actual uncertainty. Again, last time, calculator work, please. Please do like that. There we go. Okay, but now, remember, we want it to be to the same power of 10. So now we have to say, okay, if it's there, it's 1, 2, 3, 4, 5, 6, 7. So that means this is going to be 0,25 times 10 to the 7. Now I can put my values together and give a proper answer. Maybe it's not quite there yet, but we can say pressure then is 1,5 plus or minus 0,25. Does that look right to you? What did we say earlier about the value and its uncertainty? What must be the same? Great, thank you. So that means I cannot have 0,25. I need to round that off and make it 0,3, or round that up. So it's going to be plus or minus 0,3. Again, that whole thing is times 10 to the 7, and then I put my units, Newton per square meter. And there's my final